Hi students, this is going to be a learning goal about proving analytically that two trig expressions are equivalent. So your job will be to use different strategies and be able to justify each step. We've already talked about the sum and difference identities, and we're going to go ahead with page 5 and fill in some of the other identities. So we have reciprocal identities, and we have sine of theta is the same as 1 over cosecant theta. We also have cosecant theta is the same as 1 over sine theta. Those are reciprocals. Cosine theta is 1 over secant theta. Secant theta is 1 over cosine theta. And the last set here is tangent theta is the same as 1 over cotangent theta. Cotangent theta is the same as 1 over tangent theta. All right, those are called reciprocal identities. Quotient identities, tangent theta is the same as sine theta over cosine theta, and cotangent theta is the same as cosine theta divided by sine theta. This should be all fairly familiar, but we have these in our graphic organizer for reasonings and justifications. Okay, so the next thing we're going to look at, I'm going to have you write down these Pythagorean identities. And this is cosine squared theta plus sine squared theta equals 1. And there's 2 more in here, but I think what I'll leave this at is if you would like to use or learn about Pythagorean identities, you're going to go to the next video. Okay, and that'll be optional, but that is there in the folder for you if you would like to learn more about Pythagorean identities. Okay, so the first example here on page 8 is going to be strategy 1, which is factoring. Factoring will include taking out a greatest common factor and factoring if we perhaps have a quadratic or something else. So in this case, I can see that I do have a quadratic situation with the sine function. This factors into sine theta minus 2 times sine theta minus 4. And you can certainly use that area model if you like. The denominator will be sine theta plus 5 and sine theta minus 4, and that will work. Okay, so we have to justify every step we do. So in this first one, we'll just go ahead. I'm just going to put the arrows on this side. We went ahead and factored. And that's it. Okay, the next line we can see that, there are 2 factors in common in both numerator and denominator. So that works out really nicely. So sine theta minus 2 over sine theta plus 5, and that's exactly what we were trying to prove. So we made it to the end. This is what we were trying to prove, and our reason here is make ones or reduce. So reduce is fine. All right, if you'd like to pause this and try this next one, that's great. If not, I can stay here with you and do it along with you. So when I look at the numerator, I already see that there's a greatest common factor of 10. So I definitely want to take that out. That's going to make our lives much easier. Okay, and then in the denominator, I can actually take out a 15. And now, look what happens. All right, let's do our reasoning here. So this reason is just factor. And we took out those greatest common factors. Now look what we have here. We have a common factor. This whole trinomial is we don't have to even go any further. So for that one, we don't have to break it down anymore. We can already cancel it. And so we'll have 10 over 15. And our reason for this is going to be reduce or make ones. And we're going to do the same thing again. 5 goes into here twice, into here 3 times. And so we have 2/3 equals 2/3, which is what I was trying to prove. So again, for this one, we would just say reduce again. Probably you could show that on the same line if you wanted to. And then we have that proved. All right, next strategy we are going to look at is change to one or two functions. So usually we write as sine and cosine. So when we see a bunch of different functions, sometimes it will help to just clean it up to sine and cosine. Definitely keep your eye over here. Notice we want to get this equal to a cosine. Well, I see secant, I see cotangent, so that's not going to be super helpful. So let's write it in terms of sines and cosines. These first two are already sine and cosine. Secant is 1 over cosine theta, and cotangent is cosine theta divided by sine theta. Now, we just talked about what these reasons would be. There's two reasons here. This first one is reciprocal identities. So reciprocal identities. And this next one is a quotient identity. Now from here, we can see that we have a sine in the numerator and denominator, a cosine in the numerator and the denominator. So this is exactly what we want to see, because now we have cosine of theta equals cosine of theta. And our reason for this last part is just going to be to reduce or make ones. And that's our reason. All right, let's go over to this next one. So same thing here. We're trying to get to cosine and tangent. We have a secant, we have a cotangent. So just because we try this doesn't mean this is always the best idea. We're going to go ahead and give it a try, see if it helps, and it might not, and then we'll go back to the drawing board if we need to. Okay, so for this one I have secant is the same as 1 over cosine theta, and cotangent is the same as cosine theta divided by sine theta. So it doesn't instantly look better, which is okay. We can kind of keep going from here. So let's put the reason in this case. The reason is quotient identity and reciprocal identity. Again, we used one of each, that's fine. And now I'm going to actually distribute that sine of theta in. So let's see what happens when I try that. I'll have sine theta over cosine theta plus sine theta cosine theta in the numerator over sine theta in the denominator. The reason is just distributive property. Okay, now I can see that the signs here will cancel, and that's just from reducing. So let's go ahead and write that in. So we'll say sine of theta over cosine theta plus cosine theta. The reason here is just reduce. And looking again, what do I want? I want a cosine and a tangent. So I have the cosine. I almost have the tangent. Sine over cosine is tan theta plus cosine theta. So for this one, we can use our quotient identity again. Now we're super close. The right side is actually cosine theta plus tangent theta, and we have the reverse. So I am going to rearrange the terms using the commutative property. Cosine theta plus tan theta equals cosine theta plus tan theta. Check mark. And then the last thing we're going to say is commutative property. Okay. Now, strategy 3 is dividing. So strategy 3 is dividing, and we also are going to take a look a little bit here at proving some Pythagorean identities. So this is kind of a combo here. So divide, that is our strategy. So usually we want to just mess around with one side or the other. This is going to be an exception. We're going to divide both sides by sine squared theta. And what we're trying to prove is this down here. Now, if I divide by sine squared theta, let's think, why would I want to do that? Well, I really want this cotangent squared theta, right? Which looks like this. And we remember we want to split that fraction, right, when I divide. So this is going to be sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equals 1 over sine squared theta. So our reason for this is just divide. And now we can start cleaning this up. We can cancel that, and that becomes 1, which is what we actually want, plus cosine squared theta over sine squared theta is cotangent squared theta equals cosecant squared theta. And so we have several, so this is our check mark. We were able to make that match. And then this reasoning for this one, there's actually going to be several. So we're going to say, to get 1, we just reduce. And try to squeeze these all in here. Then quotient identity, and then reciprocal identity. So all 3 of those are in there, and then we were able to make that work. Okay, for the next one, I'm not going to do this one with you, but you should be able to get down here using the same method, but I want you to divide both sides, in this case, by cosine squared theta. So that's going to be your first step for the next example. Okay, I want you to recall some even-odd functions. Okay, so a little bit of recall here from previous units. If we have an input of the opposite of x, and if it's exactly equal to f of x, we know we have an even function. And if we input the opposite of x and we get the opposite of f of x, we have an odd function. So we want to recall sine is actually an odd function. Think about if I plug in pi over 2 and negative pi over 2, what are the outputs? 1 and negative 1. So sine of the opposite of theta is the opposite sine theta by definition. And also, since cosecant is reciprocal functions, cosecant is also odd, and the cosecant of the opposite of theta is the opposite of cosecant theta. Let's do the same with our cosine and tangent. Now let's think about this here. What if I plugged in pi over 4 and negative pi over 4? I get the exact same outputs. So cosine is an even function. So since it's even, cosine the opposite of theta is the same as cosine theta. We know reciprocal functions with secant theta and cosine theta. So this is also, secant is also an even function. And by definition, secant of the opposite of theta is the same as secant theta. Let's take a look at our tangent. If we plug in pi over 4 and negative pi over 4, we're going to get opposite outputs. So tangent is odd. So by definition, tangent of the opposite theta is the opposite of tan theta. And cotangent, of course, is a reciprocal function. So with tangent, so it's also odd. And so cotangent of the opposite of theta is the opposite of cotangent theta. All right, so our even and odd identities. Now we want to have these all written down here. So you'll have these in your little graphic organizer. Sine of the opposite theta is the opposite sine theta. And the reciprocal, same thing, cosecant opposite theta is the opposite of cosecant theta. Cosine of the opposite theta equals cosine theta. Secant of opposite theta is the same as secant theta. Tangent, and we're just pulling all this from that previous slides. Tangent of the opposite theta is the same as the opposite tan theta. Cotangent of the opposite theta is opposite cotangent theta. So these, let's see if we can get a lighter color here. We'll just do that one, I guess. So the outer ones are odd. And then let's get another color here. Let's do purple. And these middle ones are even. So we'll be able to use these now when we are proving our identities. Okay, so let's take a look here at page 10, and we have tangent of the opposite theta times cosine theta equals negative sine theta. So right away, I really don't want this opposite of theta as my argument. So I know tangent is an odd function. So I can write this as the opposite tangent theta times cosine theta. My reason for this is it's an odd function. The next thing we can do is we can write tangent in terms of sine and cosine. So we can say the opposite of sine theta over cosine theta times cosine theta. Eyes on the prize, this is what we're trying to prove, that it's equal to negative sine theta. All right, so this we would say quotient identity. All right, from here, hopefully we can see some canceling that can happen when we reduce. So let's see here, we'll have negative sine theta equals negative sine theta, which is what I was trying to prove. And we did this, we just did reduce, and we proved it. So you're going to use those different tools to be able to justify and prove. Okay, so there's some other ones like this that you can go ahead and try using those different even and odd identities. And then what I would like you to do for classwork to practice these, page 12, 1 and 2, page 13, 1, 2, 4, 6, and 10. And you'll be turning this in for me to take a peek at. The key is posted. Please make sure you are checking your process with the key and making any revisions as needed.